The universe is vast, mysterious, and ever-changing. A cosmic arena of creation and destruction where gravity bends light. Worlds are born, and stars die in spectacular explosions. From the swirling storms of Jupiter to the hidden ocean beneath Europa, from the rings of Neptune and Uranus to the icy edges of the Kuiper Belt, we have only just begun to uncover the truths of the cosmos. We have sent machines beyond the edges of the solar system, riding on the gravitational slings of Jupiter and Saturn. We have witnessed planets orbiting distant stars, traced the invisible pull of dark matter, and followed the echoes of ancient supernovae. But the biggest questions remain unanswered. Does life exist beyond Earth? Hidden in the frozen oceans of Europa? Locked beneath the sands of Mars? What forces truly shape the universe? The dark matter binding galaxies? The dark energy pulling them apart? How does humanity fit into this cosmic puzzle? From the first pioneers of spaceflight to the International Space Station, we have only taken the first steps into the unknown. From the legendary missions of Pioneer, Voyager and Galileo to the watchful eyes of Hubble and Chandra, we stand on the brink of a new era of cosmic understanding. This is more than a journey through space. This is a journey through time, through the forces that have shaped the past, the present and the future of the universe. Welcome to the final season, the frontiers of the cosmos.
Cosmologists believe the universe's inflation in the first 10 to 32 seconds after the Big Bang created those minute variations, which concentrated normal and dark matter into the seeds that would eventually form galaxies and stars. In 2003, the Wilkinson Microwave Anisotropy Probe WMAP Explorer mission verified and expanded upon COBE's findings, thereby contributing to developing new, precise estimates of the universe's age. Are there planets orbiting other stars? Whether planets orbit other stars has been too technologically impractical to address, resulting in Giordano Bruno's execution in 1600, or too heretical to pose throughout the history of astronomy. Nevertheless, astronomers have recently discovered a resounding affirmative to this inquiry. By the late 20th century, as telescopes and observational technology had advanced, astronomers could detect the presence of planets around other stars using various methods. One method takes advantage of the fact that planets cause their parent stars to wobble in the sky. For instance, Jupiter's gravity causes our Sun's path to appear to wobble slightly as it orbits the center of the galaxy. In 1992, astronomers discovered that they could detect such small wobbles as very slight changes in the rotational speed of rapidly spinning neutron stars known as pulsars. Using the Arecibo radio telescope, astronomers discovered a millisecond pulsar, PSR B1257+12, in the constellation Virgo in 1990. The pulses from the supernova remnant of this collapsed neutron star were monitored every 6.22 milliseconds, revealing small, consistent pulse rate fluctuations. In 1992, researchers elucidated that the gravitational pull of at least 3 planets orbiting the pulsar was responsible for this phenomenon. Based on mathematical modeling, it is probable that 2 planets are approximately 4 times the mass of Earth, while a third is approximately 2% of Earth's mass. All 3 planets are believed to be orbiting within 0.5 astronomical units of the pulsars. Most astronomers were taken aback by this initial verified evidence of extrasolar planets, as they had anticipated the discovery of planets around more conventional main sequence stars, such as the Sun, rather than around more exotic objects, such as neutron stars. The nature of these specific pulsar planets is the subject of much speculation. They may be the rocky and metallic cores of previous gas or ice giants, stripped of their outer volatile layers by the supernova explosion that generated the pulsar. Alternatively, they could result from a second round of solar nebula planet formation, which utilized the remnant materials ejected by the supernova explosion. These worlds are robustly detected, irrespective of their origins. Astronomers and planetary scientists are currently identifying and describing planets orbiting other suns. However, they must also consider a broader array of potential scenarios where extreme extrasolar planets may form and develop in various environments. Numerous astronomers expressed uncertainty regarding the solar system's conclusion beyond Neptune's orbit after Pluto's discovery in 1930. Kenneth Edgeworth, an Irish astronomer, proposed in 1943 that Pluto may be one of numerous small trans-Neptunian bodies that were unable to expand significantly due to the significant distance between early growing planetesimals, kilometer-sized clumps of dust and ice, and the consequently reduced impact rate in the outer solar system. In the 1950s, Gerard P. Kuiper, a Dutch-American planetary scientist, researched planets' formation in the outer solar system. He also proposed the existence of a vast disk of small bodies beyond Pluto. Nevertheless, Kuiper conjectured that Pluto's gravitational influence would have dispersed and cleared away this disk if Pluto were an Earth-sized body, as was previously believed. For decades, the Edgeworth-Kuiper Belt, or simply the Kuiper Belt, was a subject of speculation among astronomers. Nevertheless, the 1990s saw the emergence of super-sensitive charge-coupled device CCD detectors and giant telescopes, which enabled the search for and eventual detection of small, faint, asteroid-like bodies at distances beyond Neptune's orbit. Apart from Pluto, Charon, and potentially former members Triton and Phoebe, the first member of the Kuiper Belt was discovered in 1992 by scientists. The object, likely approximately 100 miles, 160 kilometers, in diameter, is designated 1992 QB1 and orbits between 40 and 46 astronomical units. AU, Neptune, is located at 30 AU. Astronomers have identified over 1,000 Kuiper Belt objects, KBOs, since that time. Certain objects, including 136,199 Eris, 136,472 Makemake, and 136,108 Haumea, are comparable in size to Pluto. In fact, Eris may be larger than Pluto, which partially influenced the International Astronomical Union's decision to downgrade Pluto from planet to dwarf planet status in 1996. About 10% of the known Kuiper Belt objects, including Pluto, have been discovered by scientists to have satellites. KBOs are primitive bodies containing comet-like water, methane, and ammonia ice mixtures. In 2015, the New Horizons probe will provide the first glimpse of KBOs, Pluto and Charon, and will subsequently encounter additional KBOs in the 2020s. 1610 Galileo Galilei identified the first planetary satellites beyond the Moon, orbiting Jupiter. Since then, scientists have identified numerous additional natural satellites orbiting all planets except Mercury and Venus. The discovery of a moon orbiting the diminutive dwarf planet Pluto in 1978 led numerous astronomers to question the size limit of an object for the formation of a moon. Is it possible for asteroids to have moons? Telescopic searches conducted in the 1970s and 1980s provided possible evidence for their existence. In 1992, the NASA Galileo spacecraft passed by the main belt asteroid 243 Ida en route to Jupiter, providing definitive proof. To the surprise and delight of all, Galileo's images revealed a small moon orbiting the asteroid. The moon Dactyl, 1 mile, 1.6 kilometers in width, was named by mission scientists in honor of the creatures that resided on Mount Ida on the island of Crete in Greek mythology. Planetary astronomers intensified their endeavors to discover additional moons, buoyed by the certainty that even small bodies can have moons. Scientists have since discovered moons orbiting over 200 small bodies, including Trojan asteroids of Jupiter and Kuiper Belt objects, by utilizing advanced technologies such as adaptive optics to enhance the effective resolution of ground-based telescopes and assets like the Arecibo radio telescope and the Hubble Space Telescope. More than 220 minor planet moons have been discovered by scientists, with some small bodies having 2 or 3, and Pluto having 5. There are numerous theories among planetary scientists regarding the existence of moons on bodies the size of asteroids or dwarf planets. Debris that remains and accumulates in orbit to form a satellite is knocked off by impacts on the primary asteroid. This hypothesis is corroborated by the substantial quantities of impact craters observed on the surfaces of asteroids, including 243 Ida and 433 Eros, which are the focus of the NASA Near-Earth Asteroid Rendezvous mission. Conversely, asteroids may capture other asteroids during close encounters. This is feasible for binary asteroids comparable in size and relatively close to one another, as computer models indicate. However, it is less probable in scenarios such as the Ida-Dactyl system, where one body is significantly larger. The NASA Galileo spacecraft passed by asteroid 243 Ida 1992 as it traveled through the main asteroid belt en route to its orbital mission at Jupiter. A companion moon named Dactyl, which is a mere 1 mile, 1.6 kilometers in size, was also observed in the images of the asteroid, which is 33 miles, 53 kilometers in length. The limits of telescope and instrument technology have defined the frontier of modern astronomy over the past few centuries. The necessity to observe extremely faint sources at extremely fine resolutions, to acquire spectroscopic observations over a wide range of the electromagnetic spectrum, and to accurately record observations for later detailed analysis have all pushed astronomy and astronomers to the cutting edge of optics, engineering, electronics, and software design. These sources are often located adjacent to much brighter sources. This is more apparent than the recent proliferation of massive optical telescopes at the world's most prestigious observing sites. In the late 1940s, the 200-inch 5-meter telescope mirror for the Hale telescope at Mount Palomar was cast, a feat of the then-current engineering. Despite the significant advancements in materials and mechanical engineering methods over the past few decades, the largest practical single-mirror telescope has only increased to approximately 320 inches or 8 meters due to the constraint of material strength and gravity. The light collecting area has expanded significantly, necessitating the development of novel concepts by engineers and opticians. One critical concept is segmented mirrors, which are smaller, more practical mirrors that, when assembled, resemble a single, much larger mirror. The twin 400-inch 10-meter telescopes of the W were the first large-scale experiment in segmented mirror telescopes. Atop Mauna Kea, Hawaii, is the M. Keck Observatory. A near-perfect giant parabolic reflector is formed by the individual and dynamic computer-controlled control of 36 hexagonal 70-inch 1.8-meter segments in the mirror of each telescope. 1993, Keck I emerged online, while Keck II followed suit in 1996. Since then, both have facilitated extraordinary scientific advancements. We constructed two Keck telescopes to capitalize on another advancement in giant telescope design. These telescopes were designed to combine data from two or more telescopes, electronics and software, to produce angular resolutions comparable to those of a single enormous telescope the size of an individual separation. Interferometry is the term used to describe this process. The Keck telescope is one example of the increasing number of large optical interferometer telescopes currently defining the most recent frontier in ground-based astronomy. Impacts have significantly impacted the history of climate and life in our own world, and played a fundamental role in shaping the surfaces and atmospheres of the planets. In contrast, impacts are uncommon and unpredictable in the solar system, rendering them impossible to investigate directly. This was the case until a team of astronomers identified the precise date and time at which a comet would collide with Jupiter 1 year in advance. During the summer of 1993, the Canadian astronomer David Levy, along with the American astronomers Eugene Shoemaker and Carolyn Shoemaker, reported the discovery of a peculiar string of pearls comet. Their observations indicated that the comet had recently passed near Jupiter, resulting in the fragmentation of dozens of pieces. The fragments, now collectively referred to as Comet Shoemaker-Levy 9, SL9, were on return trajectories to Jupiter and were expected to collide with the planet in July 1994, according to their data. Astronomers worldwide mobilized telescopes and space observatories to monitor the events, as this was the first time an impact event was known in advance. As anticipated, 21 cometary fragments, each measuring 0.6 to 1.2 miles, 1 to 2 kilometers, in diameter, collided with Jupiter at a velocity of 134,000 miles per hour, 60 kilometers per second, between July 16th and July 22nd. The results were unexpected and spectacular, defying the widespread predictions that such small, icy objects could produce huge fireballs, plumes, and Earth-size blemishes that would last for months. In fact, certain astronomers had anticipated that Jupiter would absorb the minute fragments without any discernible impact. How erroneous they were. The SL9 impacts on Jupiter served as a sobering reminder of the destructive potential of small bodies traveling at an extremely high velocity. Additionally, they were a media and public sensation, disseminated globally in near real time through a relatively new communication medium known as the Internet. The central core temperatures and pressures of the stars in the main sequence are sufficiently high to facilitate the nuclear fusion of hydrogen into helium, even though they vary in size and color. In fact, the minimum stellar mass that can facilitate nuclear fusion is approximately 7 to 9% of the mass of the Sun, or approximately 75 to 80 times the mass of Jupiter. In the 1970s, astronomers posited that a population of substellar objects might be too large to be classified as giant planets, but too small to be classified as stars. The reason for scientists' designation of these objects as brown dwarfs is that they would be smaller than stars and would emit infrared heat from gravitational contraction, but not their visible light from nuclear fusion. The expedition aimed to identify and describe these potentially significant connections between giant planets and small stars. Researchers identified potential candidates in the late 1980s and early 1990s. However, it was difficult to determine the distinction between brown dwarfs and small stars. In 1994, scientists identified a faint infrared source near Gliese 229, a small red dwarf star located approximately 19 light-years from our solar system, as a potential brown dwarf. The fainter object is orbiting the star, as evidenced by subsequent observations from the Hubble Space Telescope and other observatories, earning it the designation Gliese 229b GL 229b. The luminosity and temperature of GL 229b 950 kelvins are much lower than those of even the smallest main sequence stars, but they are significantly higher than those of a gas giant planet that orbits a red dwarf star approximately 30 astronomical units (AU) away. The discovery of methane in the spectrum of GL 229b, a gas unstable in stellar atmospheres, provided definitive evidence that it is not a low-mass star. GL 229b is currently estimated to be a brown dwarf with approximately 20 to 50 Jupiter masses. The masses of some of the largest planets recently discovered in orbit around other stars are approximately 20 to 50 times that of Jupiter. Does this suggest that they are brown dwarfs rather than planets? The low-mass line that separates a low-mass star and a giant megaplanet is ambiguous. Astronomers frequently employ density, infrared luminosity, or the presence of X-rays to determine the classification of a brown dwarf. However, when uncertain, they resort to the official definition, which stipulates that a brown dwarf is a star with a mass greater than 13 Jupiter masses. Astronomers were compelled to intensify their search for evidence of extrasolar planets around normal main sequences or sun-like stars following the 1992 discovery of the first extrasolar planets around pulsar B 1257+12. For decades, it has been recognized that stars in binary systems can exhibit wobbles in their proper motion across the sky because both stars orbit the system's center of mass. Theoretically, a planet comparable to Jupiter or larger and orbiting a single star should demonstrate the same types of wobbles, albeit on a much smaller scale. Astronomers achieved a significant milestone when they recognized that they did not require the precise measurement of the star's position over time. Rather, they could deduce the star's wobbling motion from its radial velocity, the wobble portion directed toward or away from Earth, using the Doppler shift of the star's spectrum. In 1995, this method discovered the first extrasolar planet that orbited the nearby Sun-like star 51 Pegasus, 51 Peg. Based on the timing of the Doppler-shifted spectral variations and the amount of wobble it induced in 51 Peg, we inferred that planet 51 Peg b is a gas giant that orbits its star at a distance of just 0.05 astronomical units and is many times the size of Jupiter. More than 500 additional planets have been discovered around nearby stars using the radial velocity method since that time. Most of these planets are called hot Jupiters, due to their large size and proximity to their parent stars. The radial velocity method is most effective for locating large planets close to hot Jupiters, but it may not be the norm. In addition to radial velocity and pulsar timing, alternative methods exist for identifying extrasolar planets. These include observing them as they pass in front of their parent stars, as part of NASA's Kepler mission, detecting them through gravitational lensing, or directly imaging them through the glare of their parent stars. Gas or ice giants continue to be the most well-known extrasolar planets. However, astronomers are currently discovering and cataloging numerous Earth-sized or super-Earth-sized worlds near Sun-like stars using these methods. Discoveries of extrasolar planets are only beginning. The Pioneer 10 and 11 and Voyager 1 and 2 flybys of Jupiter revealed a complex, enigmatic, and beautiful mini-solar system on the giant planet. This system includes a dynamic atmosphere of zones, belts, and long-lived cyclonic storm systems such as the Great Red Spot, a veritable zoo of icy and rocky satellites, including 4 that are essentially planets in their own right: Io, Europa, Ganymede, and Callisto, a dusty system of narrow rings, and an enormous magnetosphere that bathes much of the system in high-energy radiation. The discoveries made during those brief flybys persuaded the planetary scientists that the subsequent logical step would be to send a spacecraft to orbit Jupiter and remain there for an extended period. In late 1977, Congress and international support approved funding for the Jupiter Orbiter and Probe mission, which was renamed Galileo in honor of the astronomer who conducted the first telescope study of Jupiter and its moons. Galileo was launched by the Space Shuttle Atlantis in late 1989 after successfully surmounting numerous technical and financial obstacles. It slingshot out to Jupiter, where it arrived and entered orbit in December 1995, using gravity-assist flybys of Venus and Earth. During his journey through the primary asteroid belt, Galileo conducted the first close flybys of asteroids 952 Gaspra and 243 Ida. The main communications antenna's inability to open properly impeded the mission. However, mission engineers and scientists devised a new mission that utilized the backup low data rate antenna. The Galileo team guided the spacecraft through 34 elliptical orbits of Jupiter over nearly 8 years, utilizing the spacecraft's cameras, spectrometers, fields, and particle instruments. They conducted a detailed study of the rings and magnetic field, flew past large and small moons to ascertain their composition and internal structure, and released a probe into the atmosphere to convey direct measurements of composition, temperature, and pressure. Jupiter's deep atmosphere crushed and vaporized the Galileo spacecraft after its mission. However, its scientific legacy will persist, thereby maintaining the broader legacy of Galileo. Telescopic observers such as American businessman and astronomer Percival Lowell, who asserted the existence of extensive linear canals traversing the arid Martian plains, popularized the notion of Mars as a possible habitat for life in the late 19th and early 20th centuries. The media capitalized on the concept, leveraging the idea of Martian inhabitants through exceptional and critically acclaimed science fiction narratives, including the 1938 radio adaptation of H.G. Wells's The War of the Worlds. The quest for evidence of life on Mars significantly influenced 20th century exploration of the Red Planet, culminating in the development and execution of numerous sensitive organic and biological detection experiments on the 2 NASA Viking landers in 1976. The presence of organic molecules in the uppermost surface materials, subjected to intense solar UV radiation for billions of years, remains uncertain despite the general acceptance of the negative test results. No evidence of organic molecules was found at either the landing site or the parts per billion concentrate. The experiments were constrained. In 1996, a group of NASA scientists asserted a remarkable claim while examining samples from a meteorite designated ALH 84001, which originated from Mars and ultimately landed in Antarctica. Within that ancient Martian rock, they asserted, existed chemical, mineral, and geological evidence of fossilized microbes, indicating that life once existed on Mars. Astronomer Carl Sagan often asserted that extraordinary claims necessitate extraordinary evidence. In the instance of ALH 84001, most scientific communities do not consider the evidence for life to be extraordinary. NASA researchers offer non-biological interpretations for each piece of evidence. The original team continues to hold firm in their conviction. Ultimately, compelling evidence for life within ALH 84001 may be inconsequential. It is significant to observe that most scientists concur that the essential criteria for life, liquid water, heat, energy sources, and organic molecules, were all available in the environment when this rock existed on Ma. ALH 8401 indicates that it was at least capable of supporting life. Comets, small, rocky, and icy entities that sublime dramatically upon approaching the Sun, have captivated and even unsettled humanity for centuries. Certain celestial bodies, such as Halley's Comet, are observable in the sky regularly, reappearing every 76 years. Numerous others, however, manifest abruptly and at unforeseen intervals. One of the most remarkable of these unforeseen comets was Hale-Bopp, observable to a significant portion of the globe for several months in the early evening skies during the spring of 1997. In July 1995, American amateur astronomers Alan Hale and Thomas Bopp discovered Comet Hale-Bopp while approaching the Sun, yet still beyond Jupiter's orbit. The comet's orbit has been determined to be a lengthy, elliptical trajectory that requires over 2,500 years to complete a revolution around the Sun. At its maximum distance, the comet is over 370 times more distant from the Sun than the Earth. Astronomers determined that before 1997, Hale-Bopp last approached Earth in the summer of 2215 BC. This comet is categorized as young due to its composition of highly volatile ices, indicating that it has predominantly resided in the frigid outer solar system rather than the warmer regions near the Sun. The advance notice of several years regarding the comet's approach to Earth gave astronomers a unique opportunity to examine a young comet nearby for the first time. Astronomers utilized spectroscopy and additional techniques to identify rocky dust, water ice, sodium, and various molecules in the comet's ion and dust tails, including complex organic molecules previously undetected. The luminous coma of Hale-Bopp suggested that its rocky and icy nucleus is substantial for a comet, measuring approximately 37 miles, 60 kilometers, in diameter, which is roughly 6 times the size of Halley's Comet. Although Hale-Bopp does not pose a direct threat, a comet of that magnitude colliding with Earth at a velocity exceeding 50 kilometers per second would obliterate civilization and likely extinguish most life on our planet. Billions of individuals observed Hale-Bopp as it remained sufficiently luminous to be visible to the unaided eye shortly after sunset for several months. The Great Comet of 1997 received extensive media coverage, accompanied by unfounded speculation and sensationalism regarding the potential contamination of Earth by comet debris. Exquisite celestial entities or potential harbingers of catastrophe. Comets have consistently exhibited dual characteristics. The NASA Galileo mission's flybys of main belt asteroids 951 Gaspra and 243 Ida in 1991 and 1993 demonstrated that even diminutive planetary bodies possess intriguing surface characteristics in their own moons, igniting interest in a specialized space mission to examine asteroids in detail. In 1996, NASA initiated the Near-Earth Asteroid Rendezvous NEAR mission to investigate the Earth-approaching asteroid 433 Eros. During its trajectory toward Eros, NEAR obtained additional scientific data in 1997 by conducting a flyby of the substantial main belt asteroid 253 Matilda. Matilde, identified in 1885 by the prolific Austrian astronomer and asteroid researcher Johann Palisa, follows an elliptical orbit between Mars and Jupiter. Recent telescopic observations indicate that Matilda is exceedingly dark, reflecting merely 4% of the incident sunlight. Astronomers categorize Matilda differently from Gaspra and Ida, which are S-type asteroids resembling stony meteorites, due to their low albedo, the ratio of reflected light to incident sunlight, gray coloration, and spectrum with minimal features. This is due to Matilda's resemblance to a carbonaceous meteorite. The distinct spectral class of Matilda and its slow rotation, exceeding 17 days for a single axial spin, generated considerable anticipation regarding NEAR's observations. The NEAR flyby of 253, Matilde validated the asteroid's low albedo and unveiled numerous unexpected findings. Researchers approximated Matilda's density to be approximately 1.3 grams per cubic centimeter, despite capturing images of only about 60% of the asteroid. This surprisingly low number is a lot less than the normal rock density. Since the asteroid is probably too close to the Sun, and therefore too warm, for ice to exist, the most likely explanation is that Matilda has up to 50% empty space between large chunks of rock. Matilda is a permeable, debris-laden asteroid. NEAR's identification of several substantial impact craters on Matilda corroborates this notion. Had the asteroid been a solid, rocky entity, any of those impacts would have obliterated it. However, the internal pore space dissipates impact energy, allowing the asteroid to endure otherwise catastrophic strikes. The NASA Viking lander missions were unequivocal successes in Martian exploration, imparting two significant lessons for future endeavors. Firstly, scientific advantages would arise from mobility on the planet's surface instead of remaining at a singular landing site. Secondly, economically, it would be preferable to explore a planetary surface at a fraction of the multi-billion-dollar expense associated with flagship-class missions like Viking. NASA integrated these insights into its third endeavor for a Mars landing mission, the Mars Pathfinder. Initiated in 1996, Mars Pathfinder was among the inaugural missions of NASA's Better, Faster, Cheaper Discovery class, with a budget objective of merely 10 to 20% of the original Viking mission's expense. The team was tasked with landing a spacecraft on Mars at a reduced cost, while also accommodating and operating a small rover to demonstrate the advantages of mobility on the Red Planet. Employing an innovative and precarious airbag-assisted landing system, Pathfinder landed on Mars on July 4, 1997, and subsequently deployed a diminutive rover named Sojourner in honor of the 19th-century African-American abolitionist and women's rights advocate Sojourner Truth. For almost 3 months, the Pathfinder lander and Sojourner rover collected images and chemical data regarding rocks and soils at the mission's landing site in Ares Vallis, an ancient Martian outflow channel believed to have experienced a catastrophic flood early in the planet's history. Numerous geological and geochemical indicators gathered during the mission supplied evidence of the region's aqueous history. With a maximum velocity of approximately 0.022 miles per hour, 1 centimeter per second, the Sojourner rover traversed roughly 330 feet, 100 meters, along a convoluted route surrounding the lander over the mission's 83 Martian days. Nonetheless, it was an impressive exhibition of the significance of mobility in robotic exploration, as the rover was capable of photographing and chemically sampling a considerably broader array of rocks and soils at the location than the lander could have achieved independently. The 2004 landings of the next generation of Mars exploration rovers, Opportunity and Spirit, built on the successful basic design and operation principles for roving on Mars that Sojourner set up by a factor of 3. Observations from the initial Mars and Viking orbiters in the late 1970s and early 1980s yielded compelling evidence that ancient Mars was markedly different and potentially more Earth-like than contemporary Mars. NASA initiated the Mars Observer Orbiter mission in 1992 to perform comprehensive observations. Unfortunately, a rupture in the fuel line likely resulted in losing communications with the Mars Observer 3 days before it arrived at Mars. The successful deployment of NASA's Mars Global Surveyor (MGS) orbiter in 1997 reinstated a significant portion of the scientific data lost from the Mars Observer in 1993. MGS was equipped with cameras, an infrared spectrometer, a laser altimeter, and a magnetometer to systematically map the planet's geology, mineralogy, topography, and magnetic characteristics over 9 Earth years, approximately 4 Mars years. MGS measurements transformed our comprehension of Mars's surface and atmosphere, akin to the impact of Viking measurements over a decade ago. High-resolution, meter-scale images have disclosed intricate details of channels, gullies, and deltas created by the continuous flow of liquid water during early Martian history, a period characterized by a warmer and wetter climate. We conducted a global mapping of volcanic and potentially aqueous minerals and achieved a more precise measurement of the planet's topography than previously attained. We discovered evidence of a robust global magnetic field on Mars, potentially when the core was partially molten and the interior exhibited heightened geological activity. The selection of the most promising potential landing sites for the 2004 Mars exploration rovers Spirit and Opportunity was primarily based on MGS images, topographical data, and mineral discoveries. They also assisted in selecting advanced cameras and spectrometers for the 2003 European Space Agency Mars Express Orbiter and the 2006 NASA Mars Reconnaissance Orbiter. MGS lost communication in late 2006. However, its legacy persists through other orbiters and rovers. Early 20th century rocket pioneers, including Konstantin Tsiolkovsky and Robert Goddard, were among the initial figures who devised the technical specifications for orbital station habitats in ACE. For most of the century, the concept of a human outpost in Earth's orbit was primarily manifested in science fiction literature, periodicals, television programs, and films. In the 1970s, the Soviet Union initiated the deployment of 9 long-duration Salyut space research modules, subsequently constructing the Mir space station in the 1980s, the first long-duration, multi-crew outpost in space. NASA's intention to launch the U.S. space station Freedom in the 1980s has not come to fruition due to budget overruns and technical setbacks. The dissolution of the Soviet Union in 1991, technical difficulties with the Mir space station, and the substantial expenses associated with launching and operating spacecraft necessitated NASA, Russia, and other spacefaring nations to collaborate on the design and operation of a joint International Space Station, ISS, commencing in 1993. The initial element of the new ISS was a Russian electrical power, propulsion, and storage module named Zarya, which was launched into low Earth orbit, approximately 230 miles, 370 kilometers above the surface, aboard a Russian Proton rocket in November 1998. A few weeks later, the crew of the Space Shuttle Endeavour launched and attached the second component, a U.S. docking, airlock, and research module called Unity, to Raya. During the subsequent 13 years, 15 additional shuttle launches and Russian Proton and Progress rockets contributed extra solar panels, living quarters, laboratories, airlocks, and docking RTAs. Finalized in 2011, the ISS encompasses the dimensions of a U.S. football field with a cumulative mass exceeding 920,000 pounds, 420,000 kilograms, rendering it the largest artificial satellite ever. The European, Japanese, and Canadian space agencies are significant collaborators alongside the United States and Russia. The International Space Station, ISS, is a global research laboratory that utilizes its distinctive microgravity orbital environment to advance space-related medical, engineering, and astrophysical sciences. Nonetheless, it functions as a crucial outpost for establishing a permanent human presence in space, enabling us to acquire knowledge on habitation and labor, and optimally prepare for expeditions beyond low Earth orbit into deep space. In the early 20th century, physicist Albert Einstein formulated his theory of general relativity to elucidate the interplay between space, time, and matter within gravitational fields, based on the prevailing astronomical belief in a static universe. To validate his theory, Einstein had to conceive an unprecedented force, termed the cosmological constant, to counterbalance the gravitational attraction and allow the universe to remain static. In 1929, Edwin Hubble's discovery of the universe's expansion prompted Einstein to determine that his cosmological constant was superfluous. All components were well suited. However, astronomers' comprehensive examination of spiral galaxies and the dynamics of galactic clusters over the ensuing decades resulted in the unexpected identification of an invisible yet gravitationally influential substance termed dark matter, alongside the sobering acknowledgement that the majority of the universe comprises matter that eludes direct observation. Equally astonishing was the revelation by astronomers in 1998 that the universe's expansion seems to be accelerating over time. Galaxies that are closer to us, observed in the relatively modern epoch of the universe, are receding from one another at a greater velocity than exceedingly distant galaxies, which we observe from a much earlier phase in the universe's history. An invisible energy force or pressure infiltrates the vacuum of space, counteracting gravity and facilitating the ongoing expansion of space since the Big Bang. Cosmologists refer to this proposed force as dark energy. Perhaps Einstein was correct regarding his cosmological constant after all. The intrinsic nature of dark energy, or its existence, cannot be directly investigated through conventional telescopic observations. Like dark matter, its existence can only be indirectly deduced by examining its gravitational influence on ordinary matter. If dark energy is validated, it will result in a remarkable and humbling understanding of our universe. Dark energy and dark matter, which we currently lack the means to quantify or define, constitute 96% of the universe's energy, whereas ordinary matter, galaxies, stars, planets, and humanity, represents merely 4% of the cosmos. The dynamic geology and hydrology of our planet have obliterated evidence of all but a few hundred terrestrial impact craters. However, the ancient, heavily scarred surface of the Moon indicates that numerous asteroids and comets have impacted Earth historically. These high-velocity impact events discharged substantial energy and geological evidence as indicated by the fossil record, which periodically caused significant alterations to the planet's climate and biosphere. The impact rate on Earth has diminished exponentially over time. Still, the number of these events is not very low these days. For example, the Tunguska event in 1908, when a comet or asteroid exploded in the atmosphere over Siberia, and military and civilian planetary surveillance satellites see many large atmospheric fireball explosions yearly. In recent decades, there has been a significant increase in the discovery rate of small asteroids and comets, particularly among near-Earth objects, NEOs, due to the growing interest in understanding the hazards associated with cosmic impacts. Specialized telescopic surveys have detected more than 500,000 main belt asteroids and nearly 1,000 near-Earth objects, NEOs. The several hundred NEOs that may threaten life on Earth are designated with the acronym PHAs, which stands for Potentially Hazardous Asteroids. With the rise in PHA discovery rates, it became evident that there was no systematic or straightforward method to comprehend and convey the risks associated with PHA impacts. In fact, there existed considerable potential for confusion or even baseless alarm regarding this matter. In 1999, a consortium of planetary astronomers established the Neutrino Impact Hazard Scale to assess the associated risks. For newly identified potentially hazardous asteroids, PHAs, Neutrino values span from 0, indicating no risk of impact, to 10, signifying a certain impact with probable catastrophic outcomes. The majority of PHAs possess Neutrino values of 0. Subsequent observations reduce the majority of the non-zero values to 0. The current record indicates an original value of 4, a 1% or greater probability of collision, for the asteroid 99942 Apophis, which is set to pass near Earth on April 13, 2029. Astronomers have subsequently reduced the pop risk to 0, but maintain vigilant observation. In 1895, German physicist Wilhelm Röntgen identified an enigmatic type of radiation during high-voltage cathode ray tube experiments. He described X-rays as a previously unrecognized form of radiation. Ultimately, 20th century physicists determined that electrons accelerated to elevated velocities in laboratory experiments or high-energy astrophysical phenomena, such as supernova explosions, can generate X-rays. Nonetheless, the astronomical investigation of X-ray sources was significantly constrained due to the Earth's atmosphere absorbing the majority of X-rays produced by cosmic phenomena. A space-based platform was required. In '78, NASA deployed the Einstein X-ray imaging satellite to perform the inaugural space-based observations of high-energy cosmic X-ray sources. For almost 3 years, Einstein examined the sky, analyzing the intricacies of supernova explosions and detecting new X-ray sources. Astronomers pushed for a more sensitive, high-resolution X-ray space telescope mission as part of NASA's Great Observatories program. The program's 4 space telescopes allow scientists to make measurements that can't be made with Earth-based telescopes. In 1999, NASA launched the Advanced X-ray Astrophysics Facility Space Telescope, Chandra, in honor of Indian-American astrophysicist Subramanian Chandrasekhar, following over 20 years of development. Initially anticipated to function for merely 5 years, Chandra has been operational for over a decade, gathering data on supernovae, pulsars, gamma-ray bursts, supermassive black holes, brown dwarfs, and dark matter. From 1995 to 2003, NASA's Galileo Jupiter orbiter performed an extensive orbital study of the giant planet's atmosphere, magnetic field, moons, and rings. We planned the spacecraft's path to fly by the Galilean satellites, Io, Europa, Ganymede, and Callisto. This allowed us to look at their surfaces and measure their masses and gravitational fields while watching their small orbital changes. During the mission, Galileo conducted 6 close flybys of Ganymede, the largest moon in the solar system. Gravity data indicated that Ganymede possesses a differentiated interior comprising a dense core of rock and iron, a lower density mantle likely composed of ice, and an outer icy crust. The most significant revelation from the flybys was the identification of Ganymede's intrinsic magnetic field within Jupiter's robust magnetosphere. The mechanism responsible for Earth's magnetic field is thought to also produce Ganymede's magnetic field, a rotating, partially molten core composed of conductive iron. The radioactive decay of elements within the satellite's interior and tidal heating from gravitational interactions with Europa and Io generate the necessary heat to maintain a molten core. By examining Ganymede's magnetic field, Galileo scientists ascertained that the satellite's mantle possesses electrical conductivity. Because the mantle is probably mostly made of ice and there are a lot of heat sources inside the planet, the simplest explanation is that Ganymede has a large layer of salty liquid water, an ocean, about 125 miles, 200 kilometers, below the icy crust. Comparable Galileo observations of Callisto indicated preliminary evidence of a surface liquid water ocean, albeit less profound, on that moon. Could these oceans, or the subsurface ocean of Europa, support life? Although persuasive, the Galileo findings do not substantiate the existence of an ocean on Ganymede or Callisto. Upcoming missions, potentially comprising orbiters and landers, must employ radar sounding and deep drilling techniques to ascertain the presence of an ocean on Europa. Over 2 centuries of observations since the identification of Ceres, the inaugural asteroid, have discovered over 500,000 minor planets traversing the solar system. Many orbits exist within the primary asteroid belt between Mars and Jupiter. Numerous orbits are found in the Trojan asteroid clouds, preceding and trailing Jupiter's orbit, and several orbits approach or intersect that of Earth, residing much closer in. We refer to the individuals in this latter category. Approximately 9,000 near-Earth asteroids, NEAs, exceed 0.6 miles, 1 kilometer, in diameter by 10%. In 1898, German astronomer Gustav Witt and French astronomer Auguste Charlois identified the inaugural near-Earth asteroid, 433 Eros. Eros periodically approaches Earth. Indeed, its nearness facilitated the application of parallax to drive some of the earliest direct measurements of the astronomical unit, AU, the mean distance between Earth and the Sun. It is among the largest known near-Earth asteroids, NEAs, and although it presently poses no threat to Earth, future orbital perturbations could render it a hazardous object. In 1996, NASA initiated a robotic mission named NEAR, Near-Earth Asteroid Rendezvous, to investigate Eros and near-Earth asteroids, NEAs, by conducting a flyby and subsequently orbiting Eros for 1 year, utilizing CCD imaging and spectroscopy for detailed analysis. The spacecraft, designated NEAR-Shoemaker to honor planetary geologist and asteroid and comet researcher Eugene M. Shoemaker, entered the orbit of Eros in 2000 following a flyby of 253 Matilda. Eros is a substantial near-Earth asteroid approximately the size of Manhattan Island, with a rocky density of approximately 2.7 grams per cubic centimeter. Its heavily cratered ancient surface, coloration, and spectrum suggest that it contains the same primordial material as ordinary chondrite meteorites, which serve as the foundational components of Earth and other planets. The Near-Shoemaker mission, which involved a year-long mapping endeavor, concluded with a soft, low-gravity landing on Eros. It now serves as a monument to early 21st century planetary exploration. The Standard Model of 20th century physics offers a theory that links matter and energy via the interactions of elementary particles and forces. Familiar components of the Standard Model encompass the electron, a fundamental charged particle, and the photon, a fundamental particle of light. The neutron identification in 1933 resulted in the prediction and subsequent discovery of the neutrino in 1956. This prompted the hypothesis that neutrinos, akin to photons, are massless elementary particles that propagate at the speed of light, resulting in 3 flavors, electron, muon, and tau neutrinos, contingent upon the process and environment. Neutrino astronomy has emerged as a vital method for investigating high-energy phenomena in inaccessible locations, such as the interior of the Sun. Large neutrino detectors began operating in the 1960s to identify elusive neutrino particles produced by the Sun or during high-energy cosmic phenomena, such as supernova explosions. The Standard Model posits that hydrogen fusion with helium within the Sun generates electron neutrinos that are detectable by these instruments. Indeed, these detectors identified the anticipated solar neutrinos, albeit at a rate approximately 1/3 of the model's prediction. The absence of neutrinos resulted in what particle physicists termed the solar neutrino problem. Physicists prioritized resolving the solar neutrino problem, as the Standard Model's validity could hinge on their success. Theorists speculated whether neutrinos could alter their flavors or oscillate among their various types. In the 1990s, researchers developed advanced high-resolution detector experiments to enhance measurement accuracy, and in 2001, the new data disclosed an unexpected finding. Neutrinos possess mass. They have exceedingly small masses and travel slightly slower than the speed of light. Crucially, experiments demonstrated that they can oscillate among electron, muon, and tau flavors, with approximately 2/3 of the electron neutrinos generated within the Sun ultimately transforming into other flavors. The resolution of the solar neutrino problem resulted in Raymond Davis, Jr. and Masatoshi Koshiba being awarded the 2002 Nobel Prize in Physics. Furthermore, it prompted essential modifications to the Standard Model, which now incorporates oscillations of neurons and other particles. The Hubble Space Telescope, HST, was constructed as a temporal device. Observing deeper into space, it simultaneously examines a more distant past, capturing light emitted by stars and galaxies billions of years prior. Astronomers have utilized standard candles, including Cepheid variable stars and specific supernovae in remote galaxies, to employ the Hubble Space Telescope to refine Hubble's law and ascertain the cosmic expansion rate. In 2001, after a decade of observations, HST scientists declared that by reversing their calculated expansion rate, they could ascertain that the Big Bang transpired approximately 13.7 billion years ago. Simultaneously, scientists deployed a new space satellite to analyze the intricacies of the cosmic microwave background radiation from the primordial expansion of the universe. The American cosmologist David Wilkinson inspired the formation. His satellite T. Wilkinson captured high-resolution images of anisotropies in the 3 Kelvin background radiation, the remnant of the universe's expansion during the initial few 100,000 years post-Big Bang at the onset of the Dark Ages before the formation of the first stars. Remarkably, irrespective of HST or alternative methodologies, the WMAP data estimated the universe's age at 13.7 billion years. Cosmologists assert that the Big Bang occurred 13.75 plus or minus 0.11 billion years ago, based on data from HST, WMAP, and other studies demonstrating remarkable precision. The Big Bang constitutes the foundational framework of cosmology, wherein hydrogen, helium, and several other light elements were formed during the event, while heavier elements, the ultimate precursors of life, were later synthesized in stars and supernovae. Explosion, rapid inflation, deionization, reionization, slow expansion, and accelerating expansion are now pivotal milestones in cosmologists' comprehension of the universe. The timing of the Big Bang prompts additional inquiries. What was the reason for its occurrence? What existed before the inception of space and time? What will be the conclusion? Such profound inquiry challenges the limits of contemporary scientific investigation. Like all stars, the Sun derives its energy from the dynamic equilibrium between the gravitational contraction of a substantial mass and the outward pressure generated by intense nuclear fusion reactions in its core. The Sun emits radiation that supplies heat and light to the planets. However, its photosphere and chromosphere also discharge highly energetic particles into interplanetary space at elevated velocities. This stream of particles is termed the solar wind. In 1995, the European Space Agency, ESA, and NASA initiated the launch of the Solar and Heliospheric Observatory (SOHO) satellite. Utilizing high-resolution ultraviolet imagery and spectroscopy, we engineered this satellite to investigate the Sun's dynamic environment, encompassing the solar wind. SOHO consistently delivers remarkable time-lapse observations of our dynamic star. Discoveries by solar astronomers regarding the solar wind from SOHO and other research have sparked significant interest in a specialized space mission to gather these distant fragments of the Sun. Planetary scientists are particularly interested in the Sun's composition, constituting approximately 99.9% of the solar system's mass and serving as the foundational composition from which the planets originated. The Genesis mission was conceived by NASA to gather and return solar wind samples of this interest. The mission began in 2001 and went into a looping orbit around one of Earth's gravitational Lagrange points L1. Until early 2004, solar wind particles hit a specially designed sample return canister. Geochemists and solar astronomers have rigorously analyzed numerous Genesis samples that endured the 2004 canister crash in the Utah desert caused by a malfunctioning re-entry parachute. We collected and studied particles from 3 types of solar wind: fast, slow, and coronal mass ejections. This gave us a lot of surprising information about the Sun's makeup, which helped us understand how the Sun and other stars work. Galaxies, stars, planets, moons, asteroids, comets, and cosmic dust grains emit thermal infrared energy based on their temperature, composition, and environment. In recent decades, astronomers have employed advanced infrared detectors to analyze the thermal energy of these objects. Significant progress occurred in 1983 with the deployment of the Infrared Astronomical Satellite, IRAS, which performed the inaugural all-sky survey of infrared radiation emitted by celestial bodies. and subsequently in 1995 with the introduction of the Infrared Space Observatory ISO satellite, which enhanced IRAS findings through high-resolution imaging and spectroscopic observations until early 1998. IRAS and ISO made significant discoveries regarding circumstellar disks, planetary formation processes, stellar formation, and galactic evolution. Inspired by these findings, NA committed its fourth and final Great Observatory satellite to a follow-up mission of IRAS/ISO. Originally designated the Space Infrared Telescope Facility, it was subsequently renamed the Spitzer Space Telescope in honor of the American astronomer and proponent of space telescopes, Lyman Spitzer. When it was first launched in 2003, Spitzer was put into a heliocentric orbit. This meant it was close enough to Earth for regular, high-bandwidth communications, but far enough away to avoid interference from Earth's thermal background signature. Spitzer employed liquid helium to cool its instruments below 4 kelvins, rendering them highly sensitive to faint cosmic thermal energy sources. Astronomers utilized the infrared spectrum's capacity to penetrate optically dense dust to examine star-forming regions, including the Orion Nebula. They also made significant discoveries while examining quasars, galaxies, protoplanetary disks, hot young stars, extrasolar planets, and our solar system. The telescope's helium supply was depleted in 2009. However, Spitzer persists in conducting less sensitive yet distinctive measurements of numerous infrared sources and is anticipated to function for several more years. Over 3 decades of successful orbital and land investigations of Mars by Mariner and Viking missions, scientists have illustrated significant past climate changes on the red planet. The current Martian surface is exceedingly frigid, arid, and uninhabitable for life as we understand it. However, as these missions disclosed, ancient Mars has been a warmer, wetter, and possibly more Earth-like environment. Early Mars, within the initial billion years post-formation, may have contended a habitable environment conducive to the proliferation of life akin to Earth's. Planetary scientists sought to advance beyond photographic evidence of a potentially habitable early Mars by obtaining quantitative geological, geochemical, and mineralogical measurements that could serve as definitive proof. The insights acquired from the 1997 Mars Pathfinder mission demonstrated the significance of mobility in conducting geological fieldwork with robots in remote areas, resulting in the decision to pursue an extensive rover mission. In response to 2 Mars mission failures in 1999, NASA opted to mitigate risk by launching twin rovers, designated Spirit and Opportunity, in 2003 rather than a single rover. Both rovers successfully landed in early 2004 and commenced their distinct missions on opposite hemispheres of the planet. Spirit in the ancient Gusev crater, potentially a former lake site, and Opportunity in the cratered region of Meridiani Planum, where Mars Global Surveyor data indicated the presence of water-formed minerals. After years of extensive exploration in Gusev with Spirit, mission scientists identified water-bearing minerals within an ancient hydrothermal system, providing evidence of Gusev's past habitability. The team promptly discovered additional water-formed minerals such as hematite, clays, and sulfates at Meridiani, offering evidence of past habitability. Although their anticipated lifespans were merely 90 days, Spirit functioned until early 2010, while Opportunity persisted in operation and yielded new discoveries as of mid-2018. Centuries of telescopic observations and the successful flybys of Pioneer 11 and Voyagers 1 and 2 have demonstrated that Saturn is remarkably beautiful and scientifically intriguing, exhibiting significant similarities and differences compared to the other gas giants. Through its planetary exploration strategy of flyby, orbit, land, rove, and sample return, NASA initiated planning for a dedicated Saturn orbiter mission in the 1980s. The agency ultimately secured congressional approval and funding in the 1990s. In 1997, a collaborative US-European spacecraft named Cassini was launched, honoring the Italian-French astronomer Giovanni Cassini, known for his early scientific observations of Saturn, its rings, and its moons. Following gravity-assist flybys of Venus, Earth, and Jupiter, Cassini entered orbit around Saturn in 2004. The orbiter transmitted remarkable images, visible infrared and radar, and spectroscopic data until its depleting fuel reserves compelled mission controllers to deliberately descend the spacecraft into Saturn's clouds, concluding the mission in 2017. Mission scientists have made numerous significant discoveries from Cassini's over 13-year exploration of the Saturn system. We have discovered 7 new moons, some of which produce unusual three-dimensional wakes, and other formations within Saturn's extensive ring system. We have also identified active geysers emitting water vapor and organic molecules from the subsurface of the all-moon Enceladus. We have obtained the initial close-up images of the moon Phoebe, potentially a captured Centaur object. We have conducted comprehensive infrared and radar imaging and mapping of Titan's obscured surface, revealing lakes of liquid methane, ethane, or propane. And we have performed the most thorough investigations to date of Saturn's atmosphere and magnetic field. Mission controllers expressed concern that as the spacecraft depleted its fuel for adequate orientation and trajectory control, it could inadvertently collide with Enceladus or Titan, risking contamination of these astronomically significant bodies. Consequently, after the 2017 mission, they deliberately directed Cassini into Saturn's atmosphere, resulting in its incineration in a spectacular display. Comets are remarkable phenomena in the night sky, exemplified by the frequent appearance of Halley's Comet throughout history and the notably striking events of rare comets, such as Hayabusa in 1996 and Hale-Bopp in 1997. Nevertheless, most of the comet's striking displays result from reflected sunlight or gaseous emissions from their tails. Before the 1986 flyby of Halley's Comet by the European Giotto spacecraft, little was understood regarding the icy, rocky, solid nucleus of comets. This session provided evidence supporting American astronomer Fred Whipple's hypothesis that comet nuclei are small, irregular, dirty snowballs. In 1999, Planetary scientists advocated for additional robotic missions to investigate the variety of cometary orbits and their origins, including those from the Kuiper Belt, the Oort cloud, and those with orbits that interact with and occasionally collide with planets, exemplified by Shoemaker-Levy 9. The Stardust mission approached the nucleus of Comet Wild 2 and gathered minute samples of dust and gas from the comet's tail, returning them to Earth in a specialized capsule. Stardust achieved significant success. Images of Wild 2 from the January 2004 flyby disclosed a diminutive, fluffy, icy nucleus with a density below 0.6 grams per cubic centimeter, emitting jets of gas and dust and exhibiting enigmatic circular pits and ridges. In 2006, the sample canister successfully returned to Earth, disclosing millions of cometary dust grains ranging from microns to millimeters in size, along with some interstellar dust grains obtained from a distinct segment of the experiment. The analysis of comet dust has disclosed the anticipated water ice and silicate minerals and a range of organic molecules, some akin to the simple organics present in the primitive Murchison meteorite. In contrast, others possess significantly more intricate hydrocarbon chains analogous to those in organic molecules. Comets appear to be significant potential contributors to the chemistry of life. Missions such as the Giotto flyby of Halley's Comet in 1986 and the Stardust flyby of Wild 2 in 2004 demonstrated that comet nuclei are diminutive, icy entities. These bodies are notably dark, reflecting merely 3 to 5% of the sunlight that impinges upon them, comparable in darkness to charcoal. The sun's heat sublimates ice, resulting in a residue of rocky and organic particles that darken the surface. Tidal forces can fracture this surface layer, permitting fresh energy to emerge from fissures and enter the interior. In a 1999 mission proposal to NASA, some scientists asserted that if the model of a comet's surface is accurate, it would be feasible, given a sufficiently forceful impact, to devise a mission that could breach the surface lag and reveal a comet's pristine, icy materials for examination. In early 2005, NASA approved the audacious mission concept and initiated the Deep Impact mission, deploying an 815-pound, 370-kilogram copper projectile probe aimed at Comet Tempel-1. As Deep Impact got closer to Tempel-1, pictures of the comet's core showed that it was a dark, irregular object about 5 by 3 miles, 8 by 5 kilometers, in size, with geological features that were surprisingly complicated, such as possible impact craters and lobes of strangely stratified terrain. The spacecraft deployed the impactor for its crash landing on July 4, 2005, resulting in a spectacular display of cosmic fireworks. The projectile breached the lag crust and entered the comet's subsurface, dispersing a substantial ejection of ice and dust comprising clays, carbonates, and silicates. Photographs from the Deep Impact flyby spacecraft disclosed a remarkable flash and a substantial debris cloud that concealed the impact crater. Subsequent analysis of the flyby data revealed that Tempel-1 possesses a low density of 0.6 grams per cubic centimeter, suggesting a highly porous, icy internal composite. In 2006, NASA's Stardust spacecraft successfully concluded its sample return mission from Comet Wild-2. In February 2011, it conducted a CSC flyby of Tempel-1. Stardust effectively captured images of the 500-foot diameter, 150-meter, impact crater created by the Deep Impact probe's interaction 6 years prior. Saturn's moon, Titan, is the second-largest satellite in the solar system, surpassing Mercury in size, and it is the only satellite with a significant atmosphere. During the Voyager flybys of Saturn in 1980 and 1981, there were significant expectations that the surface would disclose intriguing landforms and processes. However, a dense layer of haze enveloped Titan, concealing the surface from observation at the visible wavelengths of the Voyager cameras. Spectroscopic data indicate that Titan's atmosphere predominantly comprises nitrogen N2. Methane, CH4, has a surface pressure 50% greater than Earth's sea level pressure, while its temperature is approximately 90 degrees above absolute zero. Data from Voyager and subsequent telescopic observations provided significant insights into Titan. However, many aspects remained enigmatic, prompting the inclusion of a specialized Titan exploration payload on the Cassini Saturn orbiter. Upon its launch in 1997, Cassini transported a Titan lander named Huygens in honor of the Danish astronomer Christian Huygens, who discovered Titan. On January 14, 2005, Huygens achieved successful aerobraking and parachute-assisted landing, marking it as the first lander on the surface of an outer planet. During the descent, the pre-captured remarkable images of riverine channel systems, shorelines, and dark, flat-floored plains were interpreted as lakes of liquid ethane, methane, or propane. The lander operated on the surface for approximately 90 minutes, capturing images of the unusual extraterrestrial terrain and assessing the pressure, temperature, and chemical composition. The 4 to 8-inch, 10 to 20 centimeter rocks depicted in this artist's illustration of the Huygens probe on Titan are pebbles composed of water and hydrocarbon ices, smoothed by movement in streams or lakes of liquid hydrocarbons. Images of Titan's surface captured by Huygens exhibit similarities to the Martian and terrestrial surfaces. However, significant distinctions exist. Rather than liquid water, Liquid hydrocarbons sculpt Titan's river channels and shorelines despite the strikingly analogous landforms. The rocks depicted in the images are presumably fragments of water or hydrocarbon ice, which behave like rock at extremely low temperatures. The potential future consequences of asteroids or comets on Earth threaten the entire human race. Examining minor celestial bodies and acquiring knowledge regarding their orbits and characteristics is a global undertaking. In the late 20th and early 21st centuries, space missions conducted by US, European, and Russian space agencies to comets Halley, Borrelly, Wild 2, and Tempel 1, along with asteroids Gaspra, Ida, Matilda, Os, and Lutetia, significantly enhanced our comprehension of bodies measuring kilometers or tens of kilometers in size. The Japanese Hayabusa spacecraft's mission was the inaugural endeavor to examine a diminutive asteroid comprehensively. Hayabusa, meaning falcon in Japanese, was the inaugural asteroid mission of the Japan Aerospace Exploration Agency, JAXA, and the first endeavor to achieve a robotic sample return from an asteroid. Initiated in 2003, Hayabusa employed innovative ion propulsion engines to gradually and delicately align its trajectory with a recently identified near-Earth asteroid designated 25143 Itokawa. In September 2005, the spacecraft approached Itokawa as the asteroid's insufficient gravity precluded true orbital maneuvering. It was identified as a gray, elongated, rocky entity measuring approximately 1,750 feet, 535 meters, in length. The uneven terrain of the small planet exhibited substantial boulders and unusually smooth regions. 2 months later, they instructed Hayabusa to approach the asteroid more closely, execute a gentle landing, deploy a small rover, collect surface soil and rock samples, and return a sample capsule to Earth. Is there no issue, correct? Indeed, various issues emerged. Although Hayabusa briefly touched down on the asteroid, the deployment of its rover was unsuccessful, resulting in the spacecraft descending uncontrollably from the surface before verifying its sample collection. When they re-established control, it was too late for a second attempt. They had to return the sample capsule to Ear without knowing if it was empty. In June 2010, the sample capsule successfully executed a parachute landing in Australia. After several weeks of meticulous unpacking and testing, scientists were pleased to discover approximately 1,500 minute dusty grains from Itokawa, which exhibit a chemical composition similar to certain primitive meteorites. Hayabusa achieved success. Upon its discovery in 1930, Pluto was celebrated as the 9th planet of the solar system, partly because its estimated size was comparable to Earth's. Subsequent observations over the decades and the discovery of Pluto's moon, Charon, ultimately resulted in the understanding that Pluto is a diminutive celestial body, measuring approximately 20% of Earth's diameter and possessing less than 1% of its mass. Despite years of stagnation and numerous textbooks depicting Pluto as a frigid and isolated remnant at the periphery of the solar system, Pluto retained its designation and appeal as a legitimate planet. Nonetheless, in the 1990s, it became evident that the solar system extends beyond Pluto. We have identified over 1,000 Kuiper Belt objects, KBOs, orbiting far beyond Neptune, alongside the established population of long-period comets, likely originating from the Oort cloud, and we anticipate the discovery of tens to hundreds of thousands more. Numerous entities are comparable in size to Pluto, or even exceed it. If Pluto qualifies as a planet, the possible emergence of Pluto-sized celestial bodies would significantly augment the total count of planets within the solar system. This prospect incited dismay among certain astronomers and necessitated the International Astronomical Union, IAU, to re-evaluate the classification of Pluto-sized celestial bodies. In 2006, the IAU formally reclassified Pluto and other large KBOs from planets to a new category, dwarf planets, established to acknowledge the significance of this newly identified class of small celestial bodies, while differentiating them from classical planets, which exert considerably greater influence on their environments. The demotion of Pluto elicited considerable public dissent, and numerous astronomers and planetary scientists remain perplexed and are profoundly divided regarding the new formal criteria for planetary classification. Many assert that any object sufficiently large to have attained a roughly spherical shape due to its own self-gravity, or that has undergone active internal processes resulting in the differentiation into a core, mantle, and crust, qualifies as a planet. Why not reclassify large satellites like Ganymede, Titan, and Europa, which are comparable to or exceed the size of Mercury, as planets? The debate persists regarding whether our solar system contains 8 recognized planets, or potentially 40 or more. The discovery of exoplanets has generated enthusiasm and expectation regarding the potential identification of Earth-like worlds in our cosmic vicinity. Nonetheless, the outlook has been formidable, marked by identifying the initial extrasolar planets surrounding an unusual high-energy pulsar supernova remnant. In contrast, the preponderance of later planet discoveries around main sequence stars consists of hot Jupiters, substantial gas giant planets orbiting near their host stars. Recently, scientists have identified super-Earth planets, which vary in size from a few to 10 to 15 times that of Earth, though most are near their parent stars. In 2007, at least 6 planets orbiting the star Gliese 581 were discovered, including 2 representatives of a novel class of planets, potentially habitable super-Earths. From the radial velocity fluctuations of the host star, we now deduce that the recently identified planets, designated Gliese 581c and d, possess masses ranging from 5 to 10 Earth masses. Crucially, these 2 planets revolve within the habitable zone of Gliese 581, the region around a star where an Earth-like planet can sustain liquid water on its surface. The habitable zone in our solar system ranges from approximately Venus to Mars. Planets such as Gliese 581c and d, along with others identified within their star's habitable zone, are not inherently habitable or populated. The notion of a habitable one recognizes that life, as we understand it, necessitates liquid water for its emergence and viability. If these worlds are subjected to detrimental radiation from intense solar flares, elevated to their melting point due to tidal interactions with their stars or other planets, or have all their water immobilized as frozen ice, they may not be habitable. Furthermore, instances from our solar system, including Europa, Titan, and Enceladus, demonstrate that habitable worlds may exist beyond the conventional habitable zone of alternative energy sources available to maintain the stability of liquid water on or beneath their surfaces. We know only one ideal Goldilocks planet for life as we understand it, Earth. Many astronomers, however, expect the imminent discovery of Earth 2.0 and analogous planets. At the onset of the 21st century, astronomers began refining and evaluating diverse methodologies for detecting extrasolar planets. The predominant search method, radial velocity surveys, exhibits heightened sensitivity to gas giant, Jupiter-sized planets near their host stars. Indeed, most initial discoveries have pertained to such, presumably uninhabitable, extrasolar planets. Alternative methods can detect smaller, even Earth-sized exoplanets orbiting other stars. Still, some methods, like measuring pulsars and gravitational lensing, need strange conditions that probably aren't good for life or one-of-a-kind events that make it hard to study the planets that have already been found. The most promising method for detecting Earth-sized planets near their stars depends on chance. If the geometry is optimal, these planets will periodically transit in front of their parent stars, resulting in a slight yet detectable dimming of the star's light. NASA's Kepler mission, named after the Renaissance astronomer Johannes Kepler, who formulated the fundamental laws of planetary motion, aims to identify Earth-sized exoplanets. In 2009, NASA deployed the Kepler satellite into an Earth-trailing solar orbit with the primary objective of observing 145,000 proximate main sequence stars for 3.5 years, analyzing their luminosity to detect periodic planetary transits. Kepler's 42 charge-coupled device detector constitutes the largest camera 95 megapixels ever deployed in space, capable of detecting variations in starlight as minute as 0.004%, or 1 part in 25,000. Kepler's primary mission from 2009 to 2013 produced remarkable outcomes. It validated over 2,500 exoplanets orbiting Sun-like stars, with additional astronomical techniques pending verification of nearly 5,000 more. Many of these are hot Jupiters in swift proximal orbits. Nonetheless, over 50 Earth-sized planets may be located within the habitable zone of their respective host stars. In late 2013, Kepler commenced an extended mission known as K2 to discover extrasolar planets across additional celestial regions and examine other astronomical entities. Astronomers prefer to construct telescopes on elevated remote mountain summits to minimize light pollution and to ascend above a significant portion of Earth's atmosphere. Smoke, smog, haze, water vapor, and various gases and aerosols obstruct light from reaching the surface or compromise the universe's spectroscopic measurements, constraining the quality of scientific observations conducted from the ground. Deploying telescopes in space, such as the Hubble Space Telescope or the Spitzer Infrared Observatory, represents a viable alternative. However, these projects require decades for completion and entail costs ranging from hundreds of millions to several $billion for construction. To obtain certain benefits of space-based observation platforms while minimizing costs and technical challenges, NASA established an airborne astronomy program circa 1965. Initially, Convair and Learjet aircraft were employed to transport small telescopes to commercial flight altitudes. Subsequently, beginning in 1975, the Kuiper Airborne Observatory, KAO, a modified C-141A jet equipped with a 36-inch 91-centimeter optical telescope, was utilized to observe astronomical entities from altitudes reaching 48,000 feet. KAO has achieved notable scientific advancements, including discovering Uranus's rings and a tenuous atmosphere on Pluto. NASA retired the KAO in 1995 to construct the larger and more potent stratospheric observatory for airborne astronomy, SOFIA, a modified 747 aircraft with a robust 100-inch 2.5-meter reflecting telescope. After experiencing technical difficulties and budget overruns, operating a 747 with a section removed is complex, SOFIA commenced its preliminary scientific flights in 2010. Operating at a nominal altitude of 41,000 feet, 12,500 meters, SOFIA, akin to KAO, ascends above nearly all atmospheric water vapor, facilitating a significantly broader spectrum of infrared observations than ground-based telescopes permit. Preliminary scientific observations conducted in 2010 and 2011 gathered data on Jupiter's atmosphere, the Orion Nebula, and the galaxy M82, where infrared observations can traverse much of the galaxy's dust to directly observe the formation of nascent stars. With the commencement of routine scientific observations, forthcoming SOFIA studies will encompass investigations of additional star-forming regions, protoplanetary disks, exoplanets, and comets. In the latter half of the 20th century, spectroscopy and color measurements from telescopic observations demonstrated that the main belt and near-Earth asteroids could be categorized into a limited array of compositional classes. S-type asteroids exhibit colors and spectra indicative of common planet-forming volcanic minerals, akin to those present in stony meteorites. Conversely, Darker objects with grayer hues and spectra resembling carbonaceous meteorites are classified as C-type asteroids, which exhibit spectra akin to metallic meteorites, are classified as M-types. Numerous research groups and classification systems have suggested various asteroid types. Before 2010, spacecraft had encountered S-type asteroids such as Eros, Gaspra, Ida, and Itokawa, and C-type asteroids, notably 253 Matilde, but no additional types. Consequently, it was particularly thrilling when the European Space Agency's Rosetta spacecraft conducted a close flyby of the M-type asteroid 21 Lutetia on July 10, 2010. Initiated in 2004, Rosetta is a mission to rendezvous with a comet. It will rendezvous with and deploy a lander onto the surface of the periodic comet Churyumov-Gerasimenko in 2014. Furthermore, like numerous other space mission teams, the Rosetta team has successfully conducted remarkable bonus science by traversing past additional celestial bodies en route. The Rosetta images of Lutetia indicated it was the largest asteroid encountered by spacecraft at that time, measuring 82 by 63 by 48 miles, 132 by 101 by 48 kilometers, 76 kilometers. It is among the densest, at 3 grams per cubic centimeter, indicating a potential rocky, metallic composition aligned with its M-type classification. Lutetia exhibits a visual appearance and geological characteristics akin to other asteroids captured nearby. A rugged, irregular surface extensively adorned with both relatively pristine and significantly eroded impact craters of diverse dimensions. Lutetia exhibits indications of a surface layer composed of fine-grained, mobile, impact-generated debris, referred to by planetary scientists as regolith. Rosetta flyby measurements stimulate ongoing research and discourse regarding why Lutetia's spectrum resembles metallic meteorites and the mechanisms by which small objects with such minimal gravity, less than 0.3% of Earth's, can retain fine-grained regolith materials. Following the successful 2005 mission to collide a projectile with Comet Tempel-1, engineers overseeing NASA's Deep Impact spacecraft recognized that sufficient fuel remained on board to function as a remote observatory for characterizing extrasolar planets via the transit method concurrently employed by the Kepler mission and to potentially engage with a second comet nucleus. Consequently, NASA redefined Deep Impact as a new mission, EPOXI, which signifies extrasolar planet observation and Deep Impact extended investigation. In November 2010, we aimed for EPOXI to conduct a close flyby of the nucleus of the Earth-approaching Comet Hartley, 2 after 3 Earth flybys for gravitational assistance in trajectory modifications. Identified in 1986 by Australian astronomer Malcolm Hartley, Hartley 2 is a short-period comet that orbits approximately 1.1 astronomical units and 5.9 astronomical units every 6.5 years. Short-period comets are categorized into Jupiter family comets such as Hartley 2, which have orbital periods under 20 years, and Halley family comets named after their most renowned representative, which possess periods between approximately 20 and 200 years. We hypothesized that numerous short-period comets were formerly long-period comets, their trajectories significantly modified by closely interacting with one of the gas giants. Hartley 2 may be a relatively primitive entity from the Oort cloud that recently approached Jupiter. The EPOXI data from the flyby corroborate the hypothesis of a primitive origin for Hartley 2 in the outer solar system. The images showed strong jets of ice, gas, and dust coming from the comet's peanut-shaped core, which is 1.4 miles, 2.3 kilometers, across. Spectroscopic analyses showed that the ice is mostly carbon dioxide dry ice, not water. Preliminary research indicates the potential existence of certain organic molecules, including methanol, in the ETS and extended atmosphere of Hartley 2. Based on how fast the comet's jets are removing mass and its surface ice melting, scientists think it may last for another 100 orbits, 0 years, before breaking into smaller pieces. Consequently, this small mass of primordial ice from the original solar nebula is probably a recent intruder in the inner solar system. Mercury is the most challenging of the classical planets to observe due to its proximity to the Sun. The planet has proven obstinately resistant to spacecraft exploration due to its excessively high thermal conditions, where sunlight can be 5 to 10 times more intense than Earth's. During the 20th century, a singular space mission investigated the innermost planet. Mariner 10, launched in 1973, conducted 3 loose flybys of Mercury between 1974 and 1975. Images of approximately 50% of the planet displayed a lunar-like, cratered terrain and extensive tectonic structures, indicating an initial molten surface that solidified and contracted over time. Mariner 10 also identified that Mercury possesses a robust magnetic field, probably associated with the planet's substantial, partially molten core. These compelling findings prompted planetary scientists to advocate for a specialized Mercury orbiter mission, which NASA approved for launch in 2004. Following gravity-assist flybys of Earth and Venus, along with 3 flybys of Mercury, the Mercury surface, ACE environment, geochemistry and ranging mission, MESSENGER, an acronym honoring Mercury's mythological role as the messenger of the gods, successfully entered an elliptical orbit around Mercury on March 11th. MESSENGER successfully mapped the entire planet and uncovered significant findings regarding ancient Mercurian volcanoes, craters, and tectonic formations before depleting its maneuvering fuel and colliding with the planet in 2015. Mission scientists concluded that the luminous areas observed in Mercury's poles in Arecibo radar images are permanently shadowed impact craters filled with ice rather than an unusual geochemical phenomenon. The poles are icier than previously believed, as ice occupies numerous small, uncharted shadowed craters. The European Space Agency's Bepi Colombo orbiter, scheduled for launch in 2018 and expected to achieve Mercury orbit in 2025, will utilize MESSENGER's discoveries in its planning and execution. Over 3 decades of successful Mars orbital and terrestrial investigations conducted by Mariner and Viking missions, scientists have illustrated significant historical temperature changes on the red planet. The current Martian landscape is exceedingly frigid, arid, and uninhabitable for life as we understand it. However, as shown by these missions, ancient Mars has had a warmer, wetter, and maybe more Earth-like environment. Early Mars, during the initial billion years post-formation, may have constituted a habitable environment conducive to the proliferation of life, akin to Earth's. Planetary scientists aim to advance beyond visual evidence of a potentially livable early Mars by obtaining quantitative geological, geochemical, and mineralogical measurements that could serve as definitive proof. The insights acquired during the 1997 Mars Pathfinder mission demonstrated the significance of mobility in conducting geological fieldwork with robots in remote areas, resulting in the decision to pursue a more extensive rover mission. Following the 2 Mars mission disasters in 1999, NASA opted to mitigate its risk by launching twin rovers, designated Spirit and Opportunity, in 2003 rather than a single rover. Both rovers successfully landed in early 2004 and commenced their distinct missions on opposite hemispheres of the planet. Spirit in the ancient Gusev crater, potentially a former lake site, and Opportunity in the cratered region of Meridiani Planum, where Mars Global Surveyor data indicated the presence of water-formed minerals. Following years of extensive exploration at Gusev with Spirit, mission scientists identified water-bearing minerals within an old hydrothermal system, offering compelling evidence for Gusev's historical habitability. At Meridiani, the researchers promptly discovered other water-formed minerals, such as hematite, clays, and sulfates, offering proof of prior habitability. Although their anticipated lifespans were merely 90 days, Spirit functioned until early 2010, while Opportunity persisted in operation and discovery until mid-2018. Centuries of telescopic views and the successful flybys of Pioneer 11 and Voyagers 1 and 2 have shown Saturn as aesthetically magnificent and scientifically intriguing, exhibiting significant parallels and distinctions from the other gas giants. Through its planetary exploration strategy of flyby, orbit, land, rove, and sample return, NASA initiated planning for a dedicated Saturn orbiter mission in the 1980s. The agency ultimately secured congressional approval and money in the 1990s. In 1997, a collaborative U.S.-European spacecraft named Cassini was launched, honoring the Italian-French astronomer Giovanni Cassini, who conducted some of the earliest scientific studies of Saturn, its rings, and its moons. Following gravity-assist flybys of Venus, Earth, and Jupiter, Cassini entered orbit around Saturn in 2004. The orbiter transmitted remarkable photos, visible, infrared, and radar, and spectroscopic data until its depleting fuel necessitated mission controllers deliberately descending the spacecraft into Saturn's clouds, concluding the mission in 2017. Mission scientists have made numerous significant discoveries from Cassini's almost 13-year exploration of the Saturn system. 7 new moons have been discovered, some of which create peculiar three-dimensional wakes and other formations within Saturn's many rings. We have also identified active geysers ejecting water vapor and organic compounds from the subsurface of the small moon Enceladus. We have obtained the initial close-up images of the moon Phoebe, potentially a captured Centaur object. We have conducted comprehensive infrared and radar imaging and mapping of Titan's obscured surface, revealing lakes of liquid methane, ethane, or propane. And we have performed the most thorough investigations to date of Saturn's atmosphere and magnetic field. Mission commanders expressed concern that when the spacecraft depleted its fuel for orientation and trajectory correction, it could inadvertently collide with Enceladus or Titan, risking contamination of these astronomically significant bodies. Consequently, at the mission's conclusion in 2017, they deliberately directed Cassini into Saturn's atmosphere, which ignited a magnificent conflagration. Comets can be remarkable phenomena in the night sky, as demonstrated by the many appearances of Halley's Comet throughout recorded history and the notably dramatic events of exceptional comets, such as Hyakutake in 1996 and Hale-Bopp in 1997. Nonetheless, most of the comet's striking displays result from reflected sunlight or gaseous emissions from their tails. Before the 1986 flyby of Halley's Comet by the European Giotto spacecraft, nothing was understood regarding the icy, rocky, solid nucleus of comets, which bolstered American astronomer Fred Whipple's hypothesis of comet nuclei as diminutive, irregular, dirty snowballs. In 1999, Planetary scientists advocated for additional robotic missions to investigate the variety of comet orbits and their origins, including those from the Kuiper Belt, the Oort cloud, and those with orbits that interact with and occasionally collide with planets, such as Shoemaker-Levy 9. The Stardust mission approached the nucleus of Comet Wild 2 and gathered minute samples of dust and gas from the comet's tail, returning them to Earth in a specialized capsule. Stardust had significant success. The January 2004 flyby of Wild 2 unveiled a diminutive, fluffy ice nucleus possessing a density below 0.6 grams per cubic centimeter, emitting jets of gas and dust, and exhibiting enigmatic circular pits and ridges. In 2006, the sample canister successfully returned to Earth, disclosing millions of cometary dust grains ranging from microns to millimeters in size. along with interstellar dust grains gathered in a distinct segment of the experiment. The analysis of comet dust has uncovered not only anticipated water ice and silicate minerals, but also a range of organic molecules, some akin to the simple organics present in the primitive Murchison meteorite. In contrast, others possess significantly more intricate hydrocarbon chains, comparable to those in organic molecules. Comets appear to be significant potential contributors to the chemistry of life. Missions such as the Giotto flyby of Halley's Comet in 1986 and the Stardust encounter of Wild 2 in 2004 showed that comet nuclei are little ice entities. These bodies are exceedingly dark, reflecting merely 3 to 5% of the sunlight that impinges upon them, comparable to the darkness of charcoal. The sun's radiation sublimates ice, resulting in a residue of stony and organic particles that darken the surface. Tidal forces can fracture this surface layer, permitting fresh ice to seep through the fissures into the interior. According to a mission proposal to NASA in 1999, if the model of a comet's surface is accurate, it should be feasible, given a sufficiently forceful impact, to devise a mission that breaches the surface barrier and reveals a comet's pristine, frozen elements for examination. In early 2005, NASA approved the audacious mission concept and initiated the Deep Impact mission, deploying an 815-pound, 370-kilogram copper projectile probe towards Comet Tempel-1. As Deep Impact approached Tempel-1, imagery of the comet's nucleus confirmed it to be a dark, irregular entity around 5 times 3 miles, or 8 times 5 kilometers, in dimensions, exhibiting unexpectedly intricate geological features, including potential impact craters and lobes of peculiarly stratified terrain. The spacecraft deployed the impactor for its crash landing on July 4, 2005, resulting in a spectacular cosmic display. The projectile breached the lag crust and entered the comet's subsurface, ejecting a substantial spray of ice and dust comprising clays, carbonates, and silicates. Images from the Deep Impact flyby spacecraft disclosed a remarkable flash and a substantial debris cloud that concealed the impact crater. The subsequent study of the flyby data revealed that Tempel-1 has a low density of 0.2006. NASA's Stardust probe successfully concluded its sample return mission from Comet Wild 2. In February 2011, it conducted a close flyby of Tempel-1. Stardust effectively captured images of the 500-foot diameter, 150-meter, impact crater created by the Deep Impact probe's collision 6 years prior. Saturn's moon, Titan, is the second-largest satellite in the solar system, exceeding Mercury in size and the only satellite with a significant atmosphere. During the Voyager flybys of Saturn in 1980 and 1981, there were significant expectations that the surface would disclose intriguing landforms and processes. Unfortunately, a dense layer of haze enveloped Titan, concealing the surface from observation at the visible wavelengths of the Voyager cameras. Spectroscopic measurements indicate that Titan's atmosphere predominantly comprises nitrogen N2. Methane, CH4, has a surface pressure 50% greater than Earth's sea level pressure, but its temperature is around 90 degrees above absolute zero. Data from Voyager and subsequent telescopic observations provided significant insights on Titan, yet many aspects remained enigmatic, prompting the inclusion of a specialized Titan exploration package on the Cassini Saturn orbiter. Upon its launch in 1997, Cassini transported a Titan lander named Huygens in honor of Titan's discoverer, the Danish scientist Christian Huygens. On January 14, 2005, Huygens accomplished successful aerobraking and parachute-assisted landing, marking it as the first lander on the surface of an outer planet. Throughout the descent, the probe captured remarkable images of riverine channel systems, shorelines, and dark, flat-floored plains, interpreted as lakes of liquid ethane, methane, or propane. The lander operated on the surface for around 90 minutes, capturing images of the unusual extraterrestrial terrain and assessing the pressure, temperature, and chemical composition. The rocks, measuring 4 to 8 inches, 10 to 20 centimeters, in this artist's depiction of the Huygens probe on Titan, are pebbles composed of water and hydrocarbon ices, smoothed by movement in streams or lakes of liquid hydrocarbons. The surface images of Titan captured by Huygens exhibit similarities to the Martian and Earth's surfaces. However, significant distinctions exist. Rather than liquid water, liquid hydrocarbons sculpt Titan's river courses and shorelines despite the unexpectedly analogous features. The rocks depicted in the photographs are presumably fragments of water or hydrocarbon ice, which behave like rock at extremely low temperatures. Potential future consequences of asteroids or comets on Earth pose a hazard to the entire human race. Examining minor celestial entities and acquiring knowledge regarding their orbits and characteristics is a global undertaking. In the late 20th and early 21st centuries, space missions conducted by US, European, and Russian space agencies to comets Halley, Borrelly, Wild 2, and Tempel 1, along with asteroids Gaspra, Ida, Mathilde, Eros, and Lutetia, significantly enhanced our comprehension of bodies measuring kilometers or tens of kilometers in size. The Japanese Hayabusa spacecraft's mission was the inaugural endeavor to examine a tiny asteroid in depth. Hayabusa, meaning falcon in Japanese, was the inaugural asteroid mission of the Japan Aerospace Exploration Agency, JAXA, and the first endeavor to achieve a robotic sample return from an asteroid. Initiated in 2003, Hayabusa employed innovative ion propulsion engines to gradually and delicately align its course with a recently identified near-Earth asteroid designated 25,143 Itokawa. In September 2005, the spacecraft commenced its rendezvous with Itokawa, an asteroid with insufficient gravity for true orbital maneuvering. It was shown to be a gray, elongated, stony entity measuring around 1,750 feet, 535 meters, in length. The uneven terrain of the small planet had substantial boulders and unusually smooth regions. 2 months later, they instructed Hayabusa to approach the asteroid more closely, execute a gentle landing, deploy a small rover, collect surface soil and rock samples, and return a sample capsule to Earth. This should present no difficulties. Indeed, several complications emerged. Although Hayabusa briefly touched down on the asteroid, the deployment of its rover was unsuccessful, resulting in the spacecraft ascending uncontrollably from the surface before verifying its sample collection. When they re-established control, it was too late for a second attempt. They had to return the sample capsule to Earth without ascertaining whether it was empty. The sample capsule successfully executed a parachute drop in Australia in June 2010. After several intense weeks of meticulous unpacking and analysis, scientists were pleased to discover over 1,500 minuscule dusty grains from Itokawa, with a chemical composition akin to certain primordial meteorites. Hayabusa was successful. Upon its discovery in 1930, Pluto was designated as the solar system's 9th planet due to its estimated Earth-like size. Subsequent studies over the years and identifying Pluto's moon, Charon, ultimately culminated in the understanding that Pluto is a diminutive celestial body, measuring approximately 20% of Earth's diameter and possessing less than 1% of its mass. Despite years of stagnation and numerous textbooks depicting Pluto as a frigid and isolated body at the periphery of the solar system, Pluto retained its designation and appeal as a legitimate planet. Nevertheless, in the 1990s, it became evident that the solar system extends beyond Pluto. We have identified over 1,000 Kuiper Belt objects, KBOs, orbiting far beyond Neptune, among the established population of long-period comets, presumably originating from the Oort cloud, and we anticipate the discovery of tens to hundreds of thousands more. Numerous entities are comparable in dimensions to Pluto or exceed its size. If Pluto qualifies as a planet, the possible emergence of Pluto-sized celestial bodies would significantly augment the total count of planets within the solar system. This prospect incited dismay among certain scientists and necessitated the International Astronomical Union, IAU, to re-evaluate the classification of Pluto-sized celestial bodies. In 2006, the IAU officially reclassified Pluto and other large KBOS from planets to a new dwarf planet category. This was undertaken to acknowledge the significance of this newly identified category of minor celestial bodies, while distinguishing them from classical planets, which exert considerably greater influence on their environment. The downgrading of Pluto elicited much public outrage, and even numerous astronomers and planetary experts expressed confusion. They are profoundly polarized on the new formal definition of planetary status. Many assert that any object sufficiently big to achieve a roughly spherical shape due to its self-gravity or has active internal processes that have resulted in the differentiation into a core, mantle, and crust qualifies as a planet. Why not designate massive satellites like Ganymede, Titan, and Europa, which are comparable to or exceed the size of Mercury, as planets? Whether our solar system comprises 8 recognized planets or 40 or more, the argument persists. The discovery of exoplanets has generated enthusiasm and expectation regarding the prospective identification of Earth-like worlds in our cosmic vicinity. Nonetheless, the outlook has been formidable, marked by the identification of the initial extrasolar planets surrounding an unusual high-energy pulsar supernova remnant, alongside the predominance of later planet discoveries orbiting main-sequence stars, which are predominantly hot Jupiters, substantial gas giants near their host stars. Recently, scientists have identified super-Earth planets, which vary in size from a few to 10 or 15 times that of Earth, though most are near their parent stars. In 2007, at least 6 planets around the star Gliese 581 disclosed 2 representatives of a novel planetary classification, potentially habitable super-Earths. Utilizing radial velocity fluctuations of the host star, we now deduce that the recently identified planets, designated Gliese 581c and d, possess masses ranging from 5 to 10 Earth masses. Crucially, these 2 worlds revolve within the habitable zone of Gliese 581, the region around a star where an Earth-like planet may sustain liquid water on its surface. The habitable zone in our solar system ranges from approximately Venus to Mars. Planets such as Gliese 581c and d, along with others identified within their star's habitable zone, are not inherently livable or populated. The habitable zone notion recognizes that life, as we understand it, necessitates liquid water for its emergence and viability. If these worlds are subjected to detrimental radiation from severe solar flares, heated to their melting point due to tidal interactions with their stars or other planets, or have all their water frozen as ice, they may not be livable. Furthermore, instances from our solar system, including Europa, Titan, and Enceladus, demonstrate that livable worlds may survive beyond the conventional habitable zone, provided other energy sources are available to maintain the stability of liquid water on or beneath their surfaces. We are aware of only one ideal Goldilocks planet for life as we understand it: Earth. Nevertheless, numerous astronomers expect the imminent discovery of Earth 0.0 and other worlds. At the 21st century's onset, astronomers began refining and evaluating diverse methodologies for identifying extrasolar planets. The predominant search method, radial velocity surveys, exhibits heightened sensitivity to gas giant, Jupiter-sized planets near their host stars. Indeed, most initial findings have pertained to such, presumably uninhabitable, extrasolar planets. Alternative techniques can detect smaller, including Earth-sized, exoplanets orbiting other stars. However, certain techniques like pulsar observations and gravitational lensing must be conducted in unusual locations that are likely inhospitable to life or during transient phenomena that complicate further investigation of the discovered planets. The most promising method for detecting Earth-sized planets near their stars may depend on chance. If the geometry is optimal, these planets will periodically transit in front of their parent stars, resulting in a slight yet detectable dimming of the star's light. NASA's Kepler mission, named after the Renaissance scientist Johannes Kepler, who uncovered the fundamental principles of planetary motion, aims to identify Earth-sized exoplanets. In 2009, NASA deployed the Kepler satellite into an Earth-trailing solar orbit to observe 145,000 nearby main-sequence stars for 3.5 years, analyzing their luminosity to detect periodic planetary transits. Kepler's 42 charge-coupled device detectors constitute the largest camera 95 megapixels ever deployed in space, capable of detecting variations in starlight as minute as 0.004% or 1 part in 25,000. Kepler's core mission from 2009 to 2013 produced remarkable outcomes. It validated almost 2,500 exoplanets orbiting Sun-like stars, with additional astronomical techniques pending verification for nearly 5,000 more. Numerous exoplanets are classified as hot Jupiters, characterized by their swift proximal orbits. Nonetheless, over 50 Earth-sized planets may be located within the habitable zone of their respective host stars. In late 2013, Kepler initiated an extended mission known as K2 to discover extrasolar planets in other sky areas and examine other astronomical entities. Astronomers prefer constructing telescopes on elevated remote mountain summits to minimize light pollution and to ascend above a significant portion of Earth's atmosphere. Smoke, fog, haze, water vapor, and other pollutants and aerosols obstruct light from reaching the surface or compromise the universe's spectroscopic readings, constraining the quality of scientific studies conducted from the ground. Deploying telescopes in orbit, such as the Hubble Orbit Telescope or the Spitzer Infrared Observatory, is an excellent option. Nonetheless, such projects require decades for completion and entail expenditures ranging from hundreds of millions to several billion dollars. To obtain the benefits of space-based observation platforms while minimizing costs and technical challenges, NASA established an Airborne astronomy program in 1965. Initially, Convair and Learjet aircraft were employed to transport small telescopes to commercial flight altitudes. Subsequently, beginning in 1975, the Kuiper Airborne Observatory, KAO, a modified C-141A jet equipped with a 36-inch 91-centimeter optical telescope, was utilized to observe astronomical phenomena from altitudes reaching 48,000 feet. KAO has achieved notable scientific advancements, including discovering Uranus's rings and a tenuous atmosphere on Pluto. NASA retired the KAO in 1995 to construct the larger and more potent stratospheric observatory for airborne astronomy, SOFIA, a modified 747 aircraft with a 100-inch 2.5-meter reflecting telescope. After experiencing technical difficulties and budget overruns, operating a 747 with a section removed is complex, SOFIA commenced its preliminary research flights in 2010. Operating at a 747 with a section removed is complex nominal height of 41,000 feet, 12,500 meters. SOFIA, like KAO, ascends beyond nearly all atmospheric water vapor, facilitating a broader spectrum of infrared studies than ground-based telescopes. Preliminary scientific studies conducted in 2010 and 2011 collected data on Jupiter's atmosphere, the Orion Nebula, and the galaxy M82, where infrared observations may effectively penetrate significant portions of the galaxy's dust to examine the creation of young stars. With the commencement of normal scientific observations, further SOFIA research will encompass investigations of other star-forming areas, planetary disks, exoplanets, and comets. In the latter part of the 20th century, spectroscopic and color measurements from telescopic observations demonstrated that the main belt and near-Earth asteroids may be categorized into a limited array of chemical classes. S-type asteroids exhibit hues and spectra indicative of prevalent planet-forming volcanic materials like those observed in stony meteorites. Conversely, C-type asteroids exhibit darker hues and possess colors and spectra similar to carbonaceous meteorites. M-type asteroids, characterized by spectra akin to metallic meteorites, are classified as C-type objects, among others. Numerous research groups and classification systems have proposed various asteroid kinds. Before 2010, spacecraft had only visited S-type asteroids such as Eros, Gaspra, Ida, and Itokawa, and C-type asteroid 253 Matilda, with no more types observed. Consequently, it was particularly thrilling when the European Space Agency's Rosetta probe conducted a close flyby of the M-type asteroid 21 Lutetia on July 10, 2010. Initiated in 2004, Rosetta is a mission to rendezvous with a comet. It will rendezvous with and deliver a lander onto the surface of the periodic comet Churyumov-Gerasimenko in 2014. Furthermore, like numerous other space mission teams, the Rosetta team has successfully conducted remarkable bonus scientific investigations by traversing near additional celestial bodies en route. The Rosetta photographs of Lutetia disclosed it as the largest asteroid observed by spacecraft at that time, measuring 82 by 63 by 48 miles, 132 by 101 by 60 kilometers, 76 kilometers. It is among the densest, at 3.4 grams per cubic centimeter, indicating a potential stony metallic composition aligned with its M-type categorization. Lutetia exhibits a visual appearance and geological characteristics akin to other asteroids captured nearby. A rugged, uneven surface extensively adorned with both relatively pristine and significantly eroded impact craters of diverse dimensions. Planetary scientists refer to the upper layer of fine-grained mobile debris generated by impacts on Lutetia as regolith. Measurements from Rosetta's flyby have incited extensive research and discourse regarding the reasons behind Lutetia's spectrum, resembling that of metallic meteorites, and the mechanisms by which small bodies with minimal gravity, less than 0.3% of Earth's, can retain fine-grained regolith materials. Comet Hartley 2. Following the successful 2005 mission to impact Comet Tempel 1 with a projectile, engineers overseeing NASA's Deep Impact spacecraft recognized that sufficient fuel remained on board to utilize the probe as a remote observatory for characterizing extrasolar planets via the transit method concurrently employed by the Kepler mission, and to potentially engage with a second comet nucleus. Consequently, NASA redefined Deep Impact as a new mission, EPOXI, which denotes Extrasolar Planet Observation and Deep Impact Extended Investigation. In November 2010, we aimed for EPOXI to conduct a near flyby of the nucleus of the Earth-approaching Comet Hartley, 2 after 3 Earth flybys for gravity-assist trajectory modifications. Identified in 1986 by Australian astronomer Malcolm Hartley, Hartley 2 is a short-period comet that orbits around 1.1 astronomical units and 5.9 astronomical units every 6.5 years. Short-period comets are categorized into Jupiter family comets, such as Hartley 2, which have orbital durations of less than 20 years, and Halley family comets, named for its most renowned representative, with periods ranging from approximately 20 to 200 years. We hypothesize that numerous short-period comets were formerly long-period comets, their trajectories significantly modified by a near interaction with one of the large planets. Hartley too may be a rather primitive entity from the Oort cloud that recently interacted with Jupiter. The epoxy observations from the flyby corroborate the hypothesis of a primitive genesis for Hartley II in the outer solar system. The striking epoxy photos displayed vigorous jets of ice, gas, and dust emanating from the comet's 1.4-mile, 2.3-kilometer, peanut-shaped nucleus. Spectroscopic tests indicated that carbon dioxide dry ice, rather than water, predominates in the ice. Preliminary research indicates the potential existence of certain organic compounds, including methanol, in the jets and extended environment of Hartley II. Given the present rate of mass loss from the jets and the sublimation of the surface ice, astronomers estimate that the comet may last for around 100 additional orbits, 700 years, before fragmenting into smaller components. Consequently, it seems probable that this little mass of primordial ice from the first solar nebula is in fact a recent intruder in the inner solar system. Mercury. Mercury is the most challenging of the classical planets to view due to its proximity to the Sun. The planet has proven obstinately resistant to spacecraft exploration due to its excessively high temperature conditions, where sunlight can be 5 to 10 times more intense than on Earth. During the 20th century, a singular space mission investigated the innermost planet. Mariner 10, launched in 1973, conducted 3 close flybys of Mercury between 1974 and 1975. Images of approximately 50% of the planet displayed a lunar-like cratered terrain and extensive tectonic structures, indicating an initial molten surface that cooled and contracted over time. Mariner 10 also revealed that Mercury possesses a robust magnetic field, presumably associated with the planet's substantial, partially molten core. These compelling findings prompted Planetary scientists to advocate for a specialized Mercury orbiter mission, which NASA approved for launch in 2004. Following gravity-assist flybys of Earth and Venus, as well as 3 flybys of Mercury, the Mercury surface, space environment, geochemistry, and ranging mission, MESSENGER, an acronym honoring Mercury's mythological role as the messenger of the gods, successfully entered an elliptical orbit around Mercury in March 2011. MESSENGER successfully mapped the whole planet and uncovered significant findings regarding ancient Mercurian volcanoes, craters, and tectonic formations before depleting its maneuvering fuel and colliding with the planet in 2015. Mission experts concluded that the luminous areas observed at Mercury's poles in Arecibo radar photos are permanently shadowed impact craters filled with ice, rather than an unusual geological phenomenon. The poles are icier than previously believed, as ice occupies numerous small, hitherto uncharted shadowed craters.